Yes, but let us welcome our third speaker of our session for this particle phonology afternoon. So we're very happy to have Christophe Grojean from DESI. Professor Grojean is an expert in elementary particle physics with a focus on high energy collider physics in connection to astrophysics and cosmology. So today he will be telling us about the future circular collider of physics manifesto. Please.
Okay, thanks a lot. Thanks for coming and listening to this talk about indeed the big project at CERN that will come after LHC, which is the Future Circular Collider. So I'm aware, of course, that there is a very similar project also here in China. The physics is very similar, so discussing one is discussing the other. There is a little bit of difference, of course, concerning the feasibility and the implementation in the local area. Physics is the same. Okay. So first of all, to really appreciate, why we need a future collider, we need to look at what we have learned from the LHC. And I think it can be summarized in a very similar way to what Jan explained. The LHC has discovered the Higgs and no new physics, right? Which doesn't mean really nothing. Here it's nothing in terms of BSM, but of course there is a lot of progress in our understanding of the standard model. In particular on the side of improving the measurement of the standard model process, precise measurement in flavor also, and also new frontier in aviation studies. So I think really the LHC was designed as a discovery machine, and it ended up like a precision machine. So nonetheless, there is various reasons to believe that there is something else to understand beyond the standard model. And for that, we certainly need more precision and more energy. Which means that we need, in a sense, because we have no clue exactly where to look for, right? There is not a very precise energy scale at which new physics will show up. We need really a broad and versatile and ambitious program that can really span a very different and very broad physics spectrum. So it should sharpen our knowledge of already discovered topics, and it should also push the frontier of the unknown, both at high and also at low scale, because new physics could be simply light and weakly coupled. Right? So it's not enough to really explore the energy frontier. We also need to explore the intensity frontier, where the coupling can be very light, can be very small. Right? So the Future Circular Collider, actually the integrated program, exactly fits the bill. Right? So when I'm talking about the integrated program of FCC, it means that it will really be implemented in two stages. First, there will be a collision of electron and positron, at an energy that will run between 90 GeV and 365 GeV. And this will produce a lot of Higgs boson, a lot of Z boson, and will produce also many heavy meson, top quark, and also it will be probing QCD. So it's basically the standard model factory in a sense, with a precision which is several order of magnitude better than what came out of LEP and LHC. And then after that, you will replace the electron and positron by proton, and there, depending a little bit of the magnet that will be available, you can reach 80, 85 TeV, 100 TeV, or even 120 TeV. So that will be decided, I think, by technology in maybe 20 years from now. Right? So at the end of the day, this FCC will be really inside a tunnel of 91 kilometers, which on average will be 200 meters underground, with 4 interaction points, very similar in the sense to LHC, slightly bigger. So I insisted that we want really more energy, but we also want to have more precision, right? And it should be reminded that a precision is also a discovery tool for new physics, right? And there have been many examples, many historical examples in physics about that. Let's say the discovery of Neptune really came from the study of the anomalous trajectory of Uranus, right? That couldn't be described simply by Newton's law, and And then Leverrier had this idea to say that, well, this anomalous trajectory can be explained if I add a new particle or a new planet. And he sit down using Newton's equation. Now he determines the mass and the position of Uranus. He sent a letter to his friend in Berlin. At that time, Berlin had, the most precise scientific instrument. And 3 days later, they received the letter, they point the telescope, and they found immediately the new planet. Right? So of course, nowadays it takes a little bit longer. No, it's not 3 days, but it's mostly 20 years or 30 years, to build this machine and discover new physics. The other example, of course, is also the discovery of general relativity that has been confirmed by, let's say, the trajectory, the anomalous trajectory of Mercury, that doesn't fit again the Newton's law. So there was this idea to repeat exactly the same story as Leverrier, to postulate a new planet, calculate the mass of the planet, the position of the planet. But at that time, they didn't find anything. They didn't find anything because indeed they were not a new planet, but there was new laws of physics. I mean, general relativity. So sometimes you discover new particles. Sometimes you discover new laws of physics. Right? But in any case, there is certainly a value in doing precision measurement of things that you already know. And closer to particle physics, you could also say that the Higgs boson has been discovered, at least predicted, by looking with high precision at the W and Z interaction to the quarks and the lepton. And indeed, in the standard model, if you look at all the quantum correction, you can really predict the mass of the Higgs boson that way, and it fits very well with the mass that has been observed clearly. Okay, so there is certainly one sector that requires more precision, and this is the Higgs boson, right? I mean, because the knowledge of the value of the Higgs coupling is actually essential to understand the deep structure of matter and the deep structure of the universe. There is various questions, that are associated to the values, the precise value of the Higgs coupling to the various particles of the standard model. So, for instance, if you take the lifetime of the stars, it is actually controlled by the Wick scale, and the Wick scale, or the mass of the W and the Z, emerge from those interactions of the Higgs boson with the gauge boson. Right? So this is a question that has been, to good accuracy, has been already solved by the LHC. The LHC has been established that the mass of the W and the mass of the Z indeed emerge from the interaction with the Higgs boson. But the other question, right? For instance, the size of the atom. The size of the atom is determined by the mass of the electron. Right? And within the standard model, the mass of the electron emerges from the interaction, the Yukawa interaction between the Higgs and the electron. But this is simply a theoretical input, right? A theoretical picture of the standard model. And we need to have an experimental confirmation of this fact, right? The fact that the mass of the electron really emerge or is associated to the coupling of the electron to the Higgs, right? And that's a question that the LHC has no way to answer, right? The LHC will never probe the electron Yukawa. So this is clearly here there is a need for a new machine that will be able to establish this fact. There is also the question of the stability of matter or nuclei, right? Which is telling you why, at the end of the day, the neutron is heavier than the proton, right? In such a way that the proton is actually stable. So you know that the mass of the proton or the mass of the neutron is essentially QCD, and QCD is isospin invariant, so it should predict the same mass. Of course, you have QED. So QED distinguishes the proton from the neutron, but actually it just distinguishes in the opposite side. It should make the proton heavier than the neutron. So at the end of the day, why the proton is lighter is simply because the mass of the up quark and the mass of the down quark are slightly different, right? So it's really due to the interaction of the up and down with the Higgs boson that the proton ends up lighter than the neutron, and that matter is actually stable. So again, this is a theoretical description, but we need an experimental verification of this fact that the mass of the up and the mass of the down indeed emerge from the interaction with the Higgs boson. And that's again something that the LHC won't be able to do. In that case, actually, we don't have really a good collider which is proposed that will be able to reach the standard model sensitivity to this coupling. But you will certainly improve already from the LHC. Then there is also the question of actually the dynamics of the electric phase transition, something that took place 10 to minus 10 seconds after the Big Bang, whether it's first order, second order phase transition, actually at the end of the day is determined by the way the Higgs boson interact with itself, or actually maybe a little bit more than the Higgs boson, maybe an extended Higgs sector that really controls the dynamics of this phase transition. Anyway, that's something we need to probe, right? I mean, those Higgs boson self-interaction. The LHE, or at least high luminosity LHE, will make significant progress. I mean, by looking at double Higgs production, you can already put some interesting bound on this coupling. But clearly, if you want to really determine the dynamics of the phase transition, you need to improve this sensitivity. And then there is also the question of this imbalance between matter and antimatter, which might be due to the fact that there are some interaction in the standard model beyond simply the CKM matrix, right? The phase of the CKM matrix that violates CP. And there is a lot of room actually for the Higgs interaction in particular to the fermion, to break CP, and that's something that we want to go and measure, right? So clearly there is a lot of things that the LHE cannot do. I mean, the LHE is a fantastic machine, it's already an Higgs factory. It has produced already something like 10 million of the Higgs boson, and it will produce, I think, 100 millions or so. So it's really a Higgs factory. Unfortunately, you know that all this Higgs boson cannot be reconstructed because of huge background. And you need actually another Higgs factory, right, that will produce about 1 million of Higgs boson, and Higgs boson that you can reconstruct in your detector, right? And that's exactly what FCCEE is aiming at. I mean, producing something like actually 2 million of Higgs boson and really studying carefully all these events with the Higgs boson. So it's basically 1 order of magnitude more data than LHE for what concerns the Higgs boson. But an interesting aspect is really that, it is a broad spectrum. So we will do Higgs physics. I mean, he will do it very well. But it's not only about the Higgs. It's really putting the Higgs in perspective with electric precision measurement, with flavor, etc. I mean, in a sense, exactly like, the discovery of general relativity didn't come from the careful study of the latest planet that was discovered. Actually, it came from the study of Mercury, which is a planet which is highest luminosity in a sense, because it has the shortest revolution around the sun, so you can really study with more data than the other, right? So exactly like where, I mean, maybe new physics won't come really from the study of the Higgs boson, but already come from the study of the Z boson, for instance, right? Simply because you will have higher luminosity. So I want to spend a little bit of time actually to tell you about the feasibility study for this new machine, right? So this feasibility study was launched actually as a result of the last or previous European strategy, that took place in 2019 and 2020. And the conclusion of this strategy is that, an electron-positron Higgs factory is the highest priority for next collider. Maybe, as a first step toward a very energetic machine, right? And as a result of this input from the community, the CERN Council actually approved this strategy, and the CERN management, was in charge of implementing it. And then a feasibility study was launched in 2021. It has just been completed now in 2025, and there have been a midterm review halfway. So what was the goal, the objective of this feasibility study? First of all, it was to demonstrate geological, technical, environmental, and administrative feasibility of building this tunnel. It's not an easy object that you want to put on the surface. I mean, you need to dig out, but I mean, even you need to know a little bit the structure of the land to know whether you will be able to perform this tunnel. Right? And then you, of course, also need to get the approval and all the administrative processes from the host state. I mean, both Switzerland and France. Right? I mean, CERN is a particular entity. It's an international organization. So in principle, they can do more or less what they want inside CERN. But unfortunately, this tunnel cannot fit in CERN land. So you need to go a little bit away and then Yes, you need to get some motorization. And then there is, of course, all this question of sustainability. I mean, how much carbon dioxide you are going to produce. I mean, how much electricity you need to run your machine. Whether you need to switch off electricity in Geneva when the machine is running. That's a question that you need to address before, proposing this machine to the funding agencies. And then, of course, you need also to secure the money. I mean, we can speak a little bit about money. It's a project that will cost about 15 billion of euros. So that goes actually beyond the CERN budget. So you need to secure money either by getting additional contribution from the CERN member state, or asking new member state to join, or asking private donors also to give a little bit of money to build this machine. Or ask your Chinese friend, maybe. And finally, I mean, also part of the feasibility study, but at the bottom of the list was consolidation of the physics case. I mean, why do you need this machine? What do you want to do with it, right? So about where to put this tunnel. So that was not a totally trivial exercise, right? Because at the end of the day, it's a 90-kilometer tunnel, but there is a lot of geographical constraint. First of all, you have the Jura over there, and you cannot go really in that direction. Otherwise, you need to have a very deep shaft to reach the tunnel, right? The same way over there, you have the Alps, right? Over there, you have the Lake Geneva. And further away you are going in that direction, I mean, the deepest and deepest you will have to dig again, right? So you need to stay close to Geneva. And then in this area, there is a really various ecological protected area that you cannot use for physics. So at the end of the day, it's really non-trivial to find where to fit this tunnel. And so there were a lot of studies. I mean, there were about 100 variants that were studied. The result of that is that, I mean, the size was slightly reduced from 100 kilometers. I don't know, that was a market goal, right? I mean, to 91 kilometers. So 91 kilometers is really the optimal things, taking into account not only geology, but also, I mean, surface constraint, environment, and infrastructure, How do you connect with the electricity grid? How do you connect with the various roads to bring the physicists in the tunnel and all these things, right? So this was really optimized, and at the end of the day, that result in this nice layout, right? And as I said, there will be 4 experimental points, with four experiments, and in addition, there will be 4 additional service shafts, right, where you want to bring material downstairs and things like that. Okay. Yes. So an important thing, as I say, it will be on average 200 meters underground, right? But you need to know with precision actually the structure of the land there to make sure that you can build the tunnel without, for instance, encountering water, right? So I already said, for instance, that you will go under the Lake Geneva, so clearly you have to go below the water, right? I mean, to avoid any flooding in your tunnel. So that's why there has been a lot of geological studies, with machines like that shake the earth just to know a little bit the geological structure behind it. And there is also some studies that are going on actually on the Lake Geneva with this kind of machine. So if you are taking a trip around Geneva, you can find those kind of studies at the moment, right? So most of these studies have been done actually in France. There is still some pending permits in Switzerland. Actually, as far as last week, I mean, there were still some concern that the Swiss authorities hasn't authorized all this site investigation, and that can result into a 6-month delay or things like that. And people are getting a little bit worried about it. Another consideration is actually the excavated material, because if you do the math yourself, it's a 91 kilometers tunnel. There is a diameter of 5.5 meters. So that represents something like 6.5 million cubic meter that you need to get out of the earth. And clearly, the local population doesn't want to see this excavated material in their garden. right? So you need to have a plan what to do with this excavated material. So most of this material is actually purely inert material, is what is called morass. So there are some studies that are going on actually to make use of this morass and to mix it with microbiological element to make it fertile, actually. And there have been interesting studies that have been performed. And for instance, at the last FCC conference, the people in charge of the studies actually managed to grow some plants and some flower out of this morass. Right? And it was a gift that were given to Fabiola Geniotti, red rose, by the people in charge of the studies. Right? There are other things that have also been studies is about just, for instance, about the heat that will be produced. I mean, clearly you will be running this machine, you will produce a lot of heat. What to do with this heat, right? And there is certainly some plan to use it to heat the local houses, the swimming pools, the schools. Sometimes, of course, the heat doesn't come in the right period. It will come in summer where you don't really need heat. But there are some good customers actually for the heat in the summers are just cheese factories, right? They need heat in the summers. And fortunately, there is a lot of cheese factory in the region, in the Jura and Haute-Savoie, right? So if you still want to eat some comté, you should build this machine. Anyway, the other thing that have been studied in, as I say, is a connection with a grid, electricity grid, right? And this is electricity or peak power consumption, and you will see that it will be something like in the TT bar threshold. I will discuss the physics in a moment, but the machine will run up to 365 GV, and this will need a power of the order of 300 megawatt, right? For total electricity consumption that are of the order of 2 terawatt hour for 1 year, right? And yeah, so people have studied how to bring this electricity to the machine and how to connect to the French and the Swiss electricity grid without destroying it, right? And that's a study that has been going on with the competent authorities. And as I said, there were also some studies actually where to build the road to bring the material, to bring the people. And at the end of the day, it was concluded that with the current design, you need to build only 4 new kilometers of new departmental road. And as you can see here, for instance, there is this access point here that are very close to some big highways here. So you don't need to build really the infrastructure, right, associated to it. So that's good also clearly for the environment, right? Yes, just a few things about the civil engineering. So this is a circular collider, but you can represent it as a linear collider also if you want, right? So this point is just equivalent to this one over there. And this is actually, this shows the geological structure. So most of it is indeed in the morass, where it's relatively easy to dig without any problem. But there are a few regions that involve some limestone that you cannot avoid, unfortunately. So that's a little bit more complicated, apparently, to dig in these things. But otherwise, everything has been well suited for this tunnel. And you can see here that you can see also the inclination of this machine that has been optimized really to maximize the path in morass and avoid as much as possible the limestone. And of course, here you need to go really under the lake, right? So at the end of the day, this tunnel, to make the tunnel, you will use actually tunnel boring machines. You will have eight machines. 2 of them are in each of these experimental points, and they will go into the opposite direction. So they progress at a rate of 18 meters per day, right, in the morass. So if you want to have 90 kilometers, I think you need to dig something like 8 years, right? As I say, you have 12 shafts, and at the end you will have also 2 large caverns. So large cavern, it means really larger than the current one for LHE, something like 65 meters of diameter for this cavern. And the size of those caverns, of this big cavern, are mostly dictated by the constraint of the FCCHH detector. Right? For FCCEE, you can use a small cavern which are of the same size of CMS, right? So something like 30 meters or 35 meters. And in addition, there will be a lot of additional small cavern for technical equipment. And as I say, I mean, the tunnel itself is has a diameter of 5.5 meters, and that's what you need to really put your detector, your injectors, etc., and also having some vehicle that can transport both the material and also the physicists. So what is the timeline, right? So as I say, the feasibility study was started in 2020. It just ended up now in 2025. We don't know yet the recommendation of this feasibility study, but I mean, the meeting that took place 2 weeks ago in Venice, I mean, was quite successful and really identified FCC as the leading project. And most of the national input from the various countries of member states really indicated that it's a preferred project, right? But this is still reviewed, and in particular, during this review, the CERN management should come up with a clear financial plan. And then it is expected that the CERN Council will take a decision in 2028. And then you can really launch all the approval process with the host state in such a way that the construction could start in 2033. And then you need something like 8 years indeed to dig the tunnel and to instrument this tunnel. We put your accelerator and build your detectors, right? So 2041 is the end of the LHC. So this will go in parallel with the running of the LHC. That's one advantage of having a new tunnel. You don't need to wait until the end of the LHC to dismantle it and then to install a new machine. And then the first collision is expected around 2045 or 2046. Right? And that will be a machine that will run for something like 15 years. And then you will go to FCCHH, so starting in 2070 or so. Okay, so now we can discuss a little bit about the physics overview. Skip that. So you can understand the physics just by looking at the plot that shows the luminosity as a function of the center of mass energy. And that's very characteristic to the circular collider, simply because synchrotron radiation, the luminosity decrease with the energy, while in principle for linear collider is just the opposite, the luminosity increase with the energy. But clearly, those two curves should meet around here, so around 500 GeV or 1 TeV, where indeed, at those energy, doesn't make sense to continue with a circular machine, at least with electron, and then you should use really a linear collider. But as you can see here, really the advantage of a circular collider is this fantastic luminosity at low energy, in particular the Z-pole, you have a luminosity that corresponds of the production of something like 10 to the 13 Z boson in 3 years. Right? So if you do the math, it's just repeating basically all the LEP1 data in every second minute. So this means that with this, it will be a machine that will be about 5 orders of magnitude more efficient than LEP, right? For the same power consumption, you will have a luminosity which is 10 to the 5 times higher. Right? And that's something that you can really see in this plot, just to give you really a feeling of the progress that have been going on in accelerator physics, contrary maybe to theoretical physics. You see here, the plot that indeed give this luminosity per electricity consumption, right, per electricity power. And you can see this 5 orders of magnitude at the mass of the Z, and still something like 4 orders of magnitude all the way to the WW threshold. And this doesn't come for free, right? There were really a lot of progress. The double ring collider with many benches, something that was implemented already in the LHC. There is top-up injection, which is something that had been developed for E plus E minus collider even in machines that are running in the moment, like CakeB or BEPC2. And there is this Crab-West collision scheme that increase also the luminosity, and finally the progress in radio frequency cavities, right? with various systems of cavities. So now you can convert this plot in terms of a number of events, right? I mean, okay, you make the run plan. So for instance, you will run on the Z-pole for 4 years, and indeed you will produce something like 10 to the 12, 10 to the 12 Z boson. Even at the WW threshold, where the luminosity is 1 order of magnitude smaller, but still within 2 years, you will produce something like 10 to the 8 pairs of Ws. And then finally, you want to reach the X threshold, so you want to produce the X boson. So at E plus E minus, you produce the X in association with the Z. And here, if you run for 3 years, you will produce something like 2 million of X boson. That's the dominant production mode, but there is also another production mode, which is subdominant via vector boson fusion, WW fusion. But it carries additional information. So you don't have as many Higgs boson, but you have additional information, different couplings, etc., that will be very useful at the end of the day to extract all the coupling of the Higgs boson. And then, yes, you can increase the energy with a slight modification of the accelerators this time. I mean, good thing is that here, between 90 GeV and 240 GeV, you could use the same accelerating cavities. It's actually a very nice feature that came out of the feasibility study. People have designed now this 2-cell cavities running at 400 megahertz, and basically you can really switch the energy as much as you want. You don't need to replace the cavities. You can use them totally in flexible mode between 90 GeV and 240 GeV, which has its own advantage, for instance, that you can go back in energy as much as you want. If you want to check, I don't know, something about the Z, while you are running at the X pole, you can do it in 1 day. You don't have to change and reinstall your accelerating system, etc. So for physics, it's certainly a big advantage. Of course, there is also a big advantage for people that are building those cavities, but yes, it's a very nice feature. Yes, so here it's also another plot that compare actually FCC with the other project, or the X factory that people have been thinking about for several years. So that's a plot that shows the precision of the X coupling that will be achieved in those machines. And in the y-axis you have the running time of this machine. So here you can see that first of all FCC, thing in red, has the best precision and also has the shortest running time. So here, actually, when I say it's about 8 years, so this count actually the run at 240 and the run at 365 GeV, because there is a lot of complementarity between those two runs, as I will show you in a moment later on. So 8 years, let's say, to achieve this precision of the per mil level for the X coupling. And now you can compare, for instance, to the click machine. So click is an accelerator, a linear accelerator at CERN also that was proposed in the past. And then there is this ILC that was originally, at the beginning was supposed to take place at DAISY, actually, and then he moved to Japan. And now, actually, people are dreaming maybe of bringing it back to CERN. That's a proposal that is going on at the moment. We're having a linear collider at CERN, but as we are going to see, this is not really the best machine to do if you want to do X physics. First of all, because it takes a long time, and also the precision is worse. Of course, this is the baseline for this project, but you can change the run plan. For instance, you can decide to run the machine a little bit longer, a little bit shorter. Right? And this plot actually shows the precision that you will reach depending on the running time of this machine. And you can see here, for instance, that if you want to reach the same sensitivity on the precision of the X coupling at FCC, right? If you will need something like 50 years for linear collider or for click, right? So what you can achieve at FCC in 8 years, you will need 50 years at a linear collider. Of course, nobody is telling you, that you need per mil precision in the X coupling. So maybe indeed percent precision is enough, right? In that case, indeed, you don't need to run that long. But okay. plot, compare, the different projects, assuming the output of physics. And of course, this has consequences, because maybe it's true that the linear collider, consume a little bit less energy per year, but if you need to run 50 years to run the same precision, then you need to multiply by 50 years, right? And at the end of the day, the total power consumption is actually higher. That shows, yes, as a function of the X precision, X coupling precision, the power consumption of the various projects, right? Or the cost of this machine, because there is the construction cost, but there is also the running cost, right? At the end of the day, something of the order of 600 million of Swiss francs to run the machine per year, right? So if you run 50 years, it's 25 billion, right? So even though the construction can be a little bit cheaper, at the end of the day, the total cost of the machine is actually much higher for given physics output again here. Or there is also something which is simply the amount of carbon dioxide that you will produce, right? Again, FCC seems to be the best machine as long as you are interested in getting enough physics. Of course, if you don't care about the physics, in that case, you don't construct any collider, right? And that will be the most sustainable collider at all, not collider at all. Okay. Good. So let's now try to discuss a little bit the physics landscape that will be achieved at FCCEE. So again, the physics landscape can be understood very well with this different energy prompt, at which the machine will be running. Right? So there will be clearly a run dedicated to X physics, where you will be measuring the mass of the X, the width of the X, all the X coupling, also the X self-coupling. So that's clearly the X factory aspect. There is a top, right? At the end of the day, you want to run the machine up to 365 GeV to produce a pairs of top quark. So what you will be doing there is measuring the mass of the top, with higher accuracy, measuring the width of the top, but also measuring, for instance, all the electric coupling of the top quark, right? And that will be essential, for instance, later on when FCCHH will be running, because there, you will be typically measuring some ratio, right? And because measuring the ratio, some systematic uncertainty drops out. But then, if you're measuring the ratio, you need to know the denominator to have access to the numerator. And that's where we really need FCCE, to know the denominator, and then to get access to the numerator. For example, if you want to have access to the top Yukawa, right, you measure the ratio of TTX over TTZ, and then TTZ, you normalize it from FCCE. That's why FCCH8 can reach a good sensitivity on the top Yukawa couplings, simply because it knows about the electric coupling of the top quark. And then there is another aspect that people don't necessarily appreciate, which is all this intensity frontier. The fact that you will be producing something like 10 to the 13 Z boson, right? So what can you do with those, right? First of all, you can do a very precise electric and QCD program, measuring again all these Z line shape, etc., measuring, this forward, backward asymmetry of the Z decays, measuring the mass of the W, the mass of the Z with very high accuracy. So that's certainly repeating what LEP has been doing, but with a precision, which is something like 500 times better. Because simply the statistic is much higher. You have 10 to the 5 more Z than at LEP, so compute the sensitivity that goes like 1 over square root, right? So that's one aspect, the electric sector. And then there is all the QCD aspect, right? Measuring, for instance, alpha strong, the strong coupling of QCD with high accuracy at the level of per mil, right? So something, again, improving like close to 1 order of magnitude compared to what we know from the LHC. And that will be essential, for all prediction of the cross-section. Alpha QCD is certainly a dominant parameter in all these standard model predictions. So you need to know it with high accuracy. And then there is all these non-perturbative aspects, the quark and gluon fragmentation function, or the non-perturbative QCD fraction, this showering or hadronization, etc. Then LHC is not necessarily the best machine actually to learn about that, and it's better to have a machine like FCC where you don't have initial state radiation, for instance. You have only final state radiation that allows you to have cleaner measurement in the QCD sector. And then you can also use all these Z boson that will be produced actually to do some direct search of new physics. Because you will have access to exotic decays, with a branching ratio, a branching fraction that can be very small. If you have 10 to the 13 Z boson, even if you have a branching ratio of 10 to minus 10, you will still have a lot of events in your detectors. Right? So that's simply a counting experiment, right? By having many of those, you have access to a region of parameter space, which is predicting very rare decays, let's say. And that could be the case of axion-like particle, dark photon, heavy neutral lepton, or long-lived particles. So for instance, this is a plot, that shows the sensitivity, right, on the mixing between, let's say, heavy neutral lepton and the active neutrinos, right, as a function of the mass of this heavy neutral lepton, or whatever, right-handed neutrinos, whatever. So this is some dedicated experiment, this beamed up experiment like SHIP or whatever. They are good clearly in very, very small masses of this heavy neutral lepton. But here there is a total white space, that will actually be covered by FCCEE. And what is also remarkable is that FCCEE will have the sensitivity to reach basically to reach the bottom region, which is predicted by the seesaw mechanism. Right? The seesaw mechanism tells you that the mass of mixing between the heavy neutral lepton and the active neutrino should be in this region, right, as a function of the mass. And here you see that you are basically covering the full region of parameter space which are allowed by seesaw. So I think it's important really to have sensitivity up to this line. The thickness of this line is just due to the fact that we don't know yet the exact mass of the neutrino. So otherwise it would be a pure line, but at the moment it's just a band. Right? Anyway. And then, yes, the last point is to use actually FCC as a flavor factory. Again, because, you will be producing so many Z boson, and they have a rather large branching fraction in big quark and tau leptons, that you will have a huge data sample, which is comparable or even larger than the dedicated flavor factories. Right? So for instance, you will have something like 10 to the 12 pairs of big quark or charm quark, or again 10 to the 11 pairs of tau leptons. So this means that you can really do a lot of B physics, you can do flavor, electric precision measurement, RB or forward-backward asymmetries for the B or the charm, determination of the CKM matrix element, or CP violation in neutral B mesons, etc. Right? And the same also in the tau physics. Right? So this is a nice example of things that you can perform at FCCEE, just looking at the decay mode of B0 meson into Caron on the pairs of tau. Right. In the standard model, you have a branching ratio of 10 to minus 7. The LHC bond will be of the order of 10 to minus 4. And actually at FCCEE, you can really reach a 5 sigma observation of this decay mode. In particular, looking at these different vertex, displaced vertices that you can reconstruct here in your detectors. Right. So this is the idea, but then there is the experimental problem, which is how to build actually the detector, which is convenient to do all these measurements. Right. So for instance, if you're interested in electric and QCD, you need a good particle flow algorithm. You need a good energy resolution, a good particle ID. If you're more interested into this search for this weakly coupled particles, then you need a good detector hermeticity, a good tracking and calorimetry. If you want to do flavors, then you need a good momentum resolution, a good tracker, a good verticing, tagging, energy resolution, etc. So that's actually the work which is done at the moment, is really to quantify, the detector requirement that are needed to achieve all these measurements. And I have some example. I mean, for instance, for the X, right? For the X, you need a momentum resolution of the order of relative momentum resolution of the order of 10 to minus 3 up to a PT of 50, up to a PT of the order of 50 GeV, right? if you want to do precision electric measurement, then you need an absolute normalization of the luminosity at the level of 10 to minus 4. Right? Relative normalization, so point-to-point normalization of this beam energy at the level of 10 to minus 5. Right? So again, that's the detector characteristic that you need to build. And then, yes, I have all my friends thinking about detectors that are trying to really design the detector accordingly. And there are four main concepts that are emerging at the moment. For instance, some that are based on good calorimetry or using some silicon vertex detector, or other that are using some novel liquid electric calorimeters, right? So yeah, people are really trying to put everything together to really match this detector requirement that I was mentioning before. There is some parallel going on clearly with the four detectors of LEP, right? I mean, what is Aleph, Delphi, L3, or Opal of FCC, right? There is, again, different detector technology that are emerging, and depending a little bit on the history of the group that you are working on, I mean, you're more or less driven into one or the other concept, right? Yes, I don't know, I still have a few minutes, so I can tell you a little bit more, giving you some example of measurement that will be done. I mean, I already discussed about flavor. So here you can see some samples of AV meson that will be produced, and you can see that really the characteristic, I mean, the size of the sample is actually already 10 times better than what is expected at the end of Bell 2, right? So in terms of statistics, it's really a new flavor factory. And on top of that, I mean, the beam meson that are produced, are coming with a high boost. I mean, contrary to flavor factories where you produce this beam meson close to threshold, here you will be producing those beam meson from the decays of the Z. So very boosted object with a boost factor of order 6. And that's very useful, for instance, if you want to reconstruct some object, for instance, I mean, making possible some topological reconstruction of the decay, even in presence of missing energy. Something which is difficult to do, in flavor factories, it will be very easy to do at FCCEE. So, it's opening new possibilities clearly for flavor. And just to give you an example, right? I mean, for instance, yes, some CKM element, matrix element, in particular VCB, which is actually a crucial element to normalize all this unitary triangle. So there you can have access to it via the study of the decays of the pairs of W's. Right? And at the moment, the uncertainty in the determination of this VCB is of the order 3%, and you will be improving up to maybe of the order of 0.1%, right? Depending a little bit on the tracking that will be available in your detectors. So again, more than one order of magnitude improvement. In tau physics, right? In tau physics, also things are quite dramatic. For instance, looking at a lepton flavor violation, where you have some expected limit of the order of 10 to minus 8, you will bring it to 10 to minus 10 or 10 to minus 11 at FCCEE. The tau lifetime uncertainty is also from 2000 ppm to 10 ppm. The tau mass uncertainty from 70 ppm to 14 ppm. So clearly there is a rich flavor program for a full community to join FCC. But this is not the end of the story. So if you're doing collider, that's really the 4 energy points that you have to keep in mind, right? I mean, the Z, the 90 GeV, 160 GeV for the pairs of W, 240 GeV for the Z, and then 365 GeV for the X. But you could also add additional running point. For instance, you can have a dedicated running at 125 GeV, where you will be producing the X simply as S-channel resonance. And that's exactly what you need to do if you want to determine the electron Yukawa. Because you have a direct coupling of the X to the electrons, to the positron. This is a challenge. I mean, this is a challenge because you need to know the beam energy with an accuracy which is smaller than the width of the X to really sit at the peak of the resonance, right? And that's highly non-trivial. It requires a different running mode of FCC, which is called monochromatization, where you make sure, for instance, that the fluctuation of the energy in one beam is compensated by the fluctuation of the energy in the other beam. Right? But yeah, that's certainly a fantastic measurement to be performing. You could also have a run at 270 GV, 17 GV, which is exactly the beginning of the threshold for the ZH production. And this, by looking at the behavior of this threshold, you could have a good mass measurement for the Higgs boson. Of course, you can measure the mass of the Higgs boson in a similar way to the way it is done at the LHC at 240 GV, but there is an independent measurement exactly at threshold. So that's again collider physics. You could also run below the Z, for QCD, right? In particular, for all this non-perturbative QCD measurement. But on top of that, you can also use FCC, the FCC machine, in a different way, right? For instance, you can use the electron from the injector for beam dump experiment, or you can extract the electron beam from the booster, or you can reuse the synchrotron radiation photon. Right? So you can use FCC as a new light source, right? It's a very energetic light source, yes, and very, very powerful. So there are some workshops that have been going on really to study this other science opportunity of FCC for photon science, or for instance, using this positron, right? You will be able to have some condensate of positronium, Bose-Einstein condensate of positronium. You will have a X-ray laser at 511 keV, right? So there is a lot of application for material science that is being explored at the moment using this machine. Of course, this is not the reason why we want the FCC, but once the machine is there, you can use it for many different things. So what should I tell you? Discovery potential, yeah, okay. There is a lot of new physics, direct new physics search that you can perform simply because you have a mini Z. Okay, we can go through the various models. This long-lived particle or axion-like particle, whatever. You have nice plots, things that have been studied. But okay, maybe I should skip that and discuss another aspect, which is the indirect sensitivity to new physics, right? Again, via this electric precision measurement. So clearly, yes, you will improve all the electric precision measurement, but how do you translate those measurements in terms of reach of new physics? So one way to do it is just to imagine, or to take all possible particles that have a three-level interaction with the standard model. So this has been classified. Actually, there are about 50 particles of this type that can have a three-level interaction with the standard model. So not all these particles have actually a direct impact on electric precision measurement. Some of them don't couple to the Z, so they don't affect the Z physics at tree level. Nonetheless, they will still produce higher dimensional operators at the mass scale of those interactions, and those higher dimensional interactions will run into other operators that are directly affecting Z physics. So via this running, you can actually gain sensitivity to all these particles, right? And this is exactly what has been quantified. So out of these 50 possible one-particle extension of the standard model, this is really the constraint that you can get on the masses of those new particles, assuming, for instance, that all their coupling are of order 1, right? All the constraints on the mass of these particles that are coming simply by electric precision measurement. And you can see that in this case, okay, when you have three-level interaction, clearly you have a very high sensitivity up to 100 of TeV. But even if you don't have, three-level interaction, so even if they don't affect Z physics at tree level, still via this running, right, via this renormalization group evolution, you can still get sensitivity up to 20 TeV in some cases. There is only few cases like this one, or scalars, right? This electric quadruplet. So this is some electric quadruplet that are probably not directly constrained by electric precision measurement. 5 minutes, yes, okay. Then skip that. I want to mention very quickly what you can do for X physics. At the end of the day, FCC is already solved at the X factory, so I should spend a little bit of time explaining what you can do. So I already told you that you will be producing something like 2 million of X boson at 240 GV, and an additional sample of, let's say, 400,000 X boson at 365 GeV. And actually, there is a nice complementarity between those two runs, right? Because it's two different production modes. Right? At 240 GeV, they are mostly produced in association with the Z, while at 365 GeV is mostly actually, there is another production mode which is opening up, which is vector boson fusion. Right? And here, for instance, on this plot, you can see actually the complementarity between those two runs. So, for instance, if you look here at the coupling of the X to the Z, right? So, how does it look like? Yes. So there is the light blue, is a run at 240 GeV only, and the dark blue is actually the sensitivity when you add 365 GeV in top of 240 GeV. And you can see really the improvement, in particular for the coupling to the W, the coupling of the tau, the coupling to the gluon, the coupling to the photon, also that really improve by combining those two runs. There is another improvement, which is actually on the X-half coupling. So maybe I won't have time to discuss the X-half coupling, but that's something that you cannot determine if you are running at a single energy. So if you have data only at 240 GeV, there is some flat direction that don't allow you to determine the X-half coupling. But if you run at two different energies, then you can disentangle this flat direction and gain sensitivity at the level of 20% on the X-half coupling. So that's complementarity between those two energy runs. There is also complementarity with LHC. So you know that and now compare, I think, these things. So there are various mode or decay mode, let's say, of the X that are statistically limited, in particular, the decays into photons or the decay into muons. So that's something, where the large data sample from the LHC will be very useful. Of course, LHC on itself, for instance, has some limitation. For instance, there is, you cannot absolutely normalize the coupling at the LHC because it's a hadron machine, so you are only sensitive to the production times the branching ratio, so you don't have an absolute normalization. The absolute normalization is coming from FCCE. So again, there is a nice interplay between LHC and FCC. So you use the data from FCC and you use the normalization. You use the large data sample from LHC and you use the absolute normalization for FCC. Okay. X-mass, well, I don't have time, but I mean, just to tell you that, yes, you will reach a sensitivity of the order 4 MeV, which is actually the width of the Z, right? The width of the X. And here, some studies that have been done is really the characteristic of the detectors that you need to optimize to reach this 4 MeV sensitivity on the mass. So, for instance, it's good to have a larger magnetic field, and also it's good to have a lighter trigger with silicon, for instance, compared to the drift chamber, right? So this is the kind of study that have been performed and conclude in the characteristic of the detectors. I mentioned that you will have access to the electron Yukawa. So this is the way you are doing it. Again, you run at 125 GeV, yes, and you look at the decays of the X, mostly actually in gluon, because you don't have any background in the decays of gluon. So in principle, you have this nice peak, but of course you have initial state radiation, etc., that suppress the peak a little bit. So at the end of the day, I mean, some studies have been concluded that you will run for something like 4 years at 125 GeV to reach a sensitivity of the order 4 sigma on the standard model sensitivity, standard model couplings. There are ways to improve this analysis, for instance, to use some spin asymmetry, transverse spin asymmetry, to actually improve the sensitivity, in particular in the decays into bottom or W's. Okay, so the chairman is getting impatient. I have too many slides, clearly. Electric precision moment. Conclusion. Conclusion, right. There have been a lot of progress in the course of the feasibility study. Now 4 IP is really the baseline. There is a new RF system which is totally flexible between 90 and 240 GeV. There is a good identification of other science opportunities. And really, it also shows the importance of FCCE to maximize the FCCHH physics potential. There are some people that are telling us, well, go directly to high energy. But actually, if you want to exploit, FCCHH properly, you need FCCE before, right? in the same way that you needed LEP before going to LHC. Yes, so it has a rich and broad physics potential, and I think it really perfectly fits the need of high energy physics after LHC. So now I wanted to conclude with some picture, right? This is a surface point where there will be one interaction point, actually. So this is how it looks like now in 2025, and this is the way it will look like in 20 years, right? So really the impact, I mean, there is a lot of effort that is made also to minimize really the impact on the landscape. There is another even nicer interaction point, I mean, close to Annecy, right? With a nice visitor center, even with a swimming pool, which is heated by the heat from the detectors, right? Beautiful park, yes. And yes, so you can already reserve your ticket, right? Okay, well, and I will conclude here. Thanks.
Great, thank you.
This is not generated by AI, right? I mean, this is really done by a company which is doing some studies for the environment.
We have maybe time for one question.
So this is all very nicely done now. Very ambitious, comprehensive plan. Obviously, we'd be familiar with it, but many. So it's accumulation for the last 10 years. I think. I'm just wondering. I mean, we are not talking about it now, obviously. But has there any thoughts about maybe not ultimate. We may not be able to ultimately get there. What is also a reasonable.
I mean, in terms of what? In terms of energy?
I mean, maybe little less luminosity or something.
Oh,
yeah. So is there any
sure.
another benchmark that we still achieve in
Right. I mean, yes. I mean, there is some studies that are going on clearly on the cavities. If the cavities don't perform as well as yeah. So something is not. At the end of the day, I mean, you don't need to reach all the luminosity which is promised really to achieve the physics plan, right? I mean,
there's some basic floor, right? That's what I'm asking. There's a floor we wanted to have, like 1 million gigs or something.
Yes, I mean, for instance, electric precision measurement. There is some impact, some correlation between electric precision measurement and the X, right? So let's say the sensitivity from LEP on electric precision measurement is not enough if you want to perform X physics, right? There is a degradation of the order of 20 or 50% in the X coupling determination due to the uncertainty on the Z couplings. So how much Z do you need to actually improve compared to LEP? And the answer is 10 to the 9. So you don't need teraZ, gigaZ is enough, right? So that, yeah, this kind of studies is done, yes.
So maybe we could conclude the session first.
No, the real discussion is started. Okay.